Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. All right, everyone. I am on the line with Diana Marculescu. Diana is Department Chair and Professor of Electrical and Computer Engineering at the University of Texas at Austin. Diana, welcome to the TWIML AI podcast.
Thank you for having me, Sam. I'm happy to be here.
I am super excited to have you on the show, especially since just before we started recording, you mentioned that you're a longtime listener. And I always love talking to listeners on the show and having the opportunity to host them on the show. So thank you for that. Being a longtime listener, you know the routine. I'm going to ask you to share a little bit about your background and how you came to work in machine learning.
Sure. I'm happy to do so. Actually, I've been listening to the podcast for quite some time, especially on my trips to conferences. And more than likely, currently, we're not traveling that much. However, we try to do our best to stay up to date by listening to podcasts, especially in this domain. My trajectory to working in this field is a little bit less traditional. I come from the computer hardware systems area. I've worked for more than 20 years on making computer hardware systems more efficient, especially more power efficient. And the way I got to work in machine learning in particular came from the applications side. So we've used machine learning to make or to perform power management for multi-core systems in the last decade or so. But more recently, in the last 3 to 4 years, my students and I decided to turn it around. And instead of using machine learning as an application to make computer systems more efficient, instead we turned our focus to making machine learning models more efficient such that they run better on existing computer systems, or trying to find ways to build computer systems that are more amenable to running machine learning models and applications. So that's where the whole idea of the co-design of both the machine learning model and the computer hardware system came into play. So our first publication in the field was 3 years ago, and ever since we continue to work in this field.
Great. And you recently had an opportunity to share some of what you're doing in the field at the Efficient Deep Learning in Computer Vision workshop at the recent CVPR conference, where you gave a keynote. In working in this field and talking about issues like, the efficiency of machine learning models, often questions about, the edge versus cloud come up. Did your research focus on, one or the other of these settings?
Sure. Actually, both are really important, right? So thinking about where we are now, much of the machine learning applications actually do run in the cloud. So for both training, we train them in the cloud. Much of the inference also happens in the cloud. If you're trying to run a speech recognition simple app on your phone or smartwatch, if it's not connected to the network, it's not going to be able to accomplish its task because everything does happen in the cloud. On the other hand, our work tries to democratize access to machine learning as an application such that it's pushing both inference as well as training to edge devices. So this is where the idea of making machine learning models, in particular neural networks, more efficient and more amenable to be run on tiny devices where constraints are really important. So our focus is mostly on edge devices, although, looking at the entire continuum from edge all the way to the cloud is just as important.
Mm-hmm. So your keynote at the workshop is titled Putting the Machine Back in Machine Learning, the Case for Hardware ML Model Co-Design. And it sounds like co-design is a key idea in your research. What it connotes for me is that, often we hold either the machine or the algorithm as fixed and try to optimize the other, with the constraint of the thing that we hold as fixed. And what I'm guessing here or imagining is that you're treating both of these as things that we can kind of co-optimize together. Is that the general idea of your research?
That's correct. And actually, the co-design idea has been used for quite some time in embedded systems, For a long time, the idea that you want to customize a hardware that runs the embedded software has been at the forefront for the last 15 to 20 years in the field of embedded system design. So it's not a new concept. What's new is actually putting the focus on the machine in the machine learning domain. And machine has never left, to be honest, the machine learning space, but we're just trying to put the focus back on the hardware because a lot of the focus that has been happening recently has been on the performance of machine learning applications, meaning accuracy or classification error, or things that actually tell us whether it does its job in the proper way. Putting things in a historical perspective, machine learning and in particular neural network research has been going on for quite some time, but it did not get at the level as we see today without the progress that we've seen in hardware design and everything we've seen from the single core to multi-core to GPU progress. So it's important to understand that the reason why machine learning applications have received so much attention and widespread usage is because of the hardware. But we're not going to be able to ride that wave of dissemination without support from the hardware. So our focus is to put the machine specifics and machine hardware metrics into the design process for neural networks. And when you do that, you have one half of the problem you mentioned, right? When you think about co-design, you have to add the other half of the problem. It's not just that the neural network has to be designed with the hardware in mind, but at the same time, we need to design the hardware with the application in mind, in this particular case, machine learning. So yes, co-design is the end goal. And we are not quite there yet. There's quite a few researchers working in this field, but there are a few components that are needed before we get to true co-design. And one is understanding what are the hardware metrics we need to look at, how do we expose them to the machine learning design process, and then how do we design neural network models that take that into account such that they fit the hardware that we might be able to have or we might be able to design for them. So it's actually a true cycle, iterative cycle of optimization.
You say that we need to focus on hardware and putting the hardware back into the process. And maybe I'm asking the same question again, or maybe I'm just going to provide the answer. But my sense is that there has been a lot of focus on hardware in the field. Clearly, different types of accelerators. What you're saying here is we've focused on hardware for optimizing hardware for a specific class of problems. This is going to be an accelerator that works well at, deep neural networks, as opposed to what I'm seeing in your research is a specific neural network architecture. We're going to kind of design the hardware for that, kind of design the neural network to work well with that hardware, do all of this at the same time. And overall, we're going to end up with a system that, performs better than hopefully the, things that aren't designed, so in such an integrated manner.
Mm-hmm. Yes, I mean, that's exactly the point, right? So, and you're right, there has been a lot of hardware focus lately. Maybe it started a little bit, with proxies, right? They weren't really hardware metrics. There were maybe flops, flop count, floating point operations. Maybe it was model size. Maybe it was some sort of proxy for latency. What we're trying to do is characterize or provide ways or methodologies to characterize neural networks from their latency, power, energy perspective on a given hardware, but at the same time identify ways to build hardware that minimizes those metrics, if it makes sense, right? So, but you mentioning the talk I gave at the workshop at CVPR. So one piece that is required to make this co-design process possible is the ability to characterize neural network architectures, or perhaps components thereof, in terms of their the time it takes to process those things, the energy or power it takes, and maybe come up with a joint metric that characterizes their energy efficiency or latency per correct inference, if you want. So in other words, come up with combined metrics that capture both hardware as well as accuracy in some sense. So providing that methodology for estimating power, energy, and latency for these, it's actually a piece of software, right, that you write, is one of the steps that allows us to identify the right configuration or architecture for the neural network. Because you can't optimize what you cannot model or characterize, right? And actually, it's easier. It's actually pretty easy to do that. We've done this for quite some time in the computer hardware embedded system domain. It's much harder to have the similar kind of model for accuracy. We can't tell how accurate is a neural network until we actually train it. On the other hand, for a given architecture, we can easily tell what the power or latency will be for a given hardware platform once you characterize it, right? So it's a very low-hanging fruit that we should take advantage of.
Mm-hmm. The idea there is expressed in some research that you've done called neural power. Is that
correct?
The one? Yeah. And we've previously talked about, characterized neural networks in terms of, things like depth and parameters and layers. Mm-hmm. And we talk about hardware in this totally different language, which is flops and power and things like that. And you're trying to kind of unify the way that we're able to talk about this. And you're doing it using a neural network. Is that right?
We use machine learning for that. So we build models for latency and power that we fit using data that we collect from a lot of synthetically generated neural networks and constructs, right? Because we look at different types of convolutional layers, fully connected layers, pooling layers, things that you typically find in neural networks, deep neural networks. So we try to build a power and a latency model, and of course also an energy model that captures all those components. And then in a composable fashion, you're able to say, once you've done this characterization and you fit the model once, you can tell just by looking at the configuration of the network, the latency end-to-end for an inference will be this much, and the power consumption will be this much. And I don't even have to run it, right? So you collect the data, you fit the model once, and then you use it over and over again. And the good thing about this is that you can use it in the optimization process when you do, say, architecture search. Architecture search is very time-consuming. But the fact that you can characterize every single component or block of this architecture space in a zero cost, O of one kind of complexity, it's really appealing because it allows you to put it in this iterative optimization process. So that's where we took this expertise in characterizing hardware metrics and used it to identify neural architectures that satisfy hardware constraints. So this is the second part of the talk that I had that talked about neural architecture search using a single path approach. And inside that iterative optimization loop, we did have this kind of latency model. In that particular case, we were looking at latency on a very specific hardware platform, Pixel 1.
And so is the idea that if you're applying neural architecture search without the metrics that you have available via neural power, you would have to run this long and expensive process and come up with a bunch of candidate models that after the fact you have to see if they satisfy your hardware constraints. But here you're able to integrate it in, and in doing so, just kind of cut off some dead ends that your search process might need to run through.
Yes, that's right. So you can prune the search process by removing candidates that do not meet maybe your latency constraints, right? You want to have each inference take less than a few tenths of a milliseconds, right? By having this characterization done once and use it over and over, you can prune the search process. You can also, the way we did it, we actually incorporated in our loss function a term that captures the cost in terms of latency. And by doing so, we're able to basically make the neural architecture search process hardware aware. And there are other components to the approach that we've had, because it relies on the concept of a super network that actually shares weights across multiple different types of structures. But I mean, that's one component. But the reason why it's actually pretty powerful is because it identifies networks that satisfy these hardware constraints, in this case latency, while at the same time doing this in a very efficient fashion. So like you said, instead of identifying a bunch of candidates that satisfy accuracy, and then we check, does it satisfy latency constraints, we're able to do this through just a single process. So it's more efficient.
Mm-hmm. There's some property of the search space that tells you that if you are looking at a particular model and it doesn't meet your power constraints, some evolution of that, not to assume that you're using evolutionary models in here, won't then be better than the thing that you're looking at, like a convexity property or something like that. Is that an assumption, or is that something that is just kind of demonstrably true about, these, search spaces for some set of models?
Yeah. So I think it's an excellent question. We just started to scratch the surface on that. Our particular approach is a differentiable search approach, meaning we cast the problem as a differentiable function, and then you just use anything that works on that, like a typically stochastic gradient descent will make convexity assumptions, although they might hold in reality, but it works pretty well in practice. In our case, you're absolutely right. The efficiency of architecture search comes from two components. One is the search space. So what are the components that we actually allow to be the building blocks for our neural network? So that's one. And the second is, how do we do the search? And you did allude to, say, evolutionary algorithms. There's also reinforcement learning that you can use. We use a differentiable approach in which all the choices that we make in terms of the architecture, although they are discrete choices, we perform a transformation that allows us to do differentiable search on them. So apply optimization algorithms that typically are used on those kinds of objective functions. So the closest or the earliest work that is in the same kind of vein as us is DARTS, which does differentiable architecture search for neural networks. The difference in our case is the search space. So the basic components that we consider is broader. But at the same time, the way we identify the different selections that take us to the final architecture is done such that we share much of the, so for example, for 3x3, 5x5, 7x7 convolutional kernel, we basically share all the weights. So the only thing we need to know for a 5x5 is that we use the 3x3 plus the outer layer that takes us to 5x5. So in some sense, it's less for us to identify. It puts more constraints on the search process, but it's more efficient in the kinds of things that it can find out. So, and it is able, so our work that was published at the ECML PKDD conference last September in Germany, and we extended it for a journal paper this year. It allows us, this more efficient search process allowed us to find a more accurate neural architecture than in the case where you would have more freedom to search. So I guess it's a fine balance between the exploitation and exploration, and we were able to find that somehow, and at the same time satisfying these hardware constraints in terms of latency. And interestingly, at the time when we did our comparisons, we were able to be better in terms of accuracy compared to the manual, so to speak, designs like MobileNet V2, V3. That, I mean, they're manual, they're zero cost, so to speak, but there was a lot of engineering time, a lot of hours spent by engineers behind those efforts. So I wouldn't want to call them zero time search costs, but they're manual, single designs, and then we did even better in terms of the search cost and accuracy compared to other types of neural architecture approaches. So because of that, we were able to, because of the efficient search space and the way we searched, so the two components put together, we were able to push the search time to hours as opposed to days. So I think that's where the strength came in only a few epochs. We were able to find this kind of architecture. So those are the two strengths are one, ability to characterize hardware metrics inside the optimization process, as well as the second component, which is the more efficient search process overall.
Is the resulting architecture that you are comparing to whatever your baseline is, the output of the single path network architecture search process, or do you also, apply other processes to that, like quantization or pruning or, compression, other compression techniques?
Sure. Single path NAS does just that, the former. So whatever you said, it identifies the architecture. But of course, on top of that, you can perform other things like quantization, compression. There's an interesting question as to whether doing this sequentially, so first identifying the architecture and then performing compression and or quantization, leads us to a better result rather than doing it together. I think there's some emerging work in that space. We're also looking at ways to identify how quantization or precision might play a role in this architecture search process. But to answer your question, you can do this. So once you identify a neural architecture, you can apply quantization. You can apply model compression or pruning, right? Those are techniques that exist. Going back to the presentation I had at the CVPR workshop, we did present some of the ideas that we had in that space, especially as they relate to quantization, as well as to pruning, channel pruning. And so in the quantization space, the idea, there's been quite a bit of work, ranging from binarized neural networks all the way to using limited precision, fixed point, limiting the number of bits for representation. Our idea was actually pretty simple. So we published first on this in 2017, and then ever since we refined that further. We wanted to limit the number of bits representing weights to a fixed number. And it turned out that in practice, using just 1 or 2 bits is sufficient to get the best in terms of efficiency, but still not miss much in terms of accuracy. So the idea is that for each weight, we identify the combination of 2 powers of 2 that, when stochastically rounded, give you the best accuracy. So we have a few examples in the original paper where we show how using stochastic rounding actually, on average, will give you, in theory, will give you the same accuracy as the original unquantized neural network. So we call these light-NN, so lightweight neural networks. And light-NN-K uses K bits to represent the weights. We still maintain the activations in the original precision. And it turns out that you can get to up to 2 orders of magnitude reduction in the either power, memory, storage, and still maintain the original accuracy. So this is pretty powerful. This was for CIFAR-10 data set, and then we extended it for ImageNet. Of course, the downside for using a quantized model is that to actually get these benefits, you will need to build an accelerator that relies on replacing every multiply, accumulate, or MAC operation with these logic operators that just do shifts and adds, right? And GPUs are not readily doing that. You could program CPUs to do that, but might take some effort. So I think what is out there right now is that if you're going to use this type of quantization, you will need to build a specialized piece of hardware to do it. So there will be true accelerators. But I think the results are pretty encouraging for us to continue to do so, because it does achieve quite a bit of energy and hardware efficiency in general for not much of a loss in accuracy. From the other perspective, you could also do pruning, right? So you could consider how you want to prune the network. You don't want to lose much in the accuracy, but you want to simplify the model even further. Our work in that space, and actually that work was just published in the conference in CVPR as an oral presentation. The idea is, so the name we used is Ledger. Basically is using a layer-based global ranking to identify where do we want to do pruning? So we do pruning based on importance. So we don't want to prune uniformly across the board. We want to prune only where accuracy is not going to suffer the most. And by doing so, you're able to achieve additional efficiency on the model side. And of course, that translates into hardware efficiency as well.
So was the name of that paper, Ledger, an intentional head fake to get people excited about some Bitcoin quantization approach?
Hopefully. I think we need to ask my student why he chose that. I like the name.
Going back to neural power and this model for the metrics, you touched on the data source, but can you elaborate on that a little bit? Did you run a bunch of simulations? Did you pull power data off of actual hardware running, some suite of models? That sounds very expensive and hard. How did you collect data to fit a model?
Yeah, so that's an excellent question. We actually did a lot of profiling. So we started with one GPU platform, and then we added more GPU platforms. And like I said, we use machine learning to build the power and latency models. So we needed a lot of data to train those models. So we relied on profiling on several GPU platforms. We profiled power, we profiled latency, we profiled also memory usage, although we did not use it explicitly, except for a component in one of our in our models. And also at the same time, we had to profile a lot of these synthetic neural networks that exhibited different types of combinations of convolutional and fully connected and pooling layers, right? So it took a lot of effort. That's true. The idea, though, is if you are using any of those platforms, you can use data that we collected. But of course, if you want to use your own platform, you can use our methodology. So our code is available. You can use your own platform, perform the same type of profiling, and then fit your own power and latency model. So it's a methodology that allows us and others allows everyone to apply on different types of platforms. But it is data intensive. Once you collect the data, though, it's just a one-time kind of thing.
Great. And you did that for, is it a handful of GPU architectures and I guess how specific is a particular model that you developed to a hardware platform? Is it kind of the architecture family, or is it a specific model or generation of a platform? How well does it generalize as the hardware evolves?
Right. I think that's an excellent question. So a methodology is as good as its potential use, right? So, and I always get this question. So, okay, neural power is good, but if I can't use it for my own platform, or if I can't generalize to other types of computer hardware platforms that don't even exist, how is this going to be used? Or how is it going to be usable? And the answer is, I think this is where the co-design comes into the picture, right? So we've built this methodology on an existing platform. However, if you are in the business of building specialized computer hardware for machine learning applications, you have an idea, you have a blank canvas that you can start from. Maybe not as blank, maybe you start from some components that you want to use. But the idea is that you can decide how you put together this architecture. And there are a lot of interesting ways to characterize a platform in terms of latency and power before it's even built, right? This is what we've done for many years before. We haven't started, we don't build computer systems by building one and then measuring power and latency. We know what those numbers will be at design time, right? So the same approach can be used in this case. I really think computer hardware designers as well as machine learning model developers have to work together, because that's where the strength comes from, and that's where the generalizability comes from. You're going to be able to get the expertise from both and come up with ways to do the actual true code design. So it's a hard problem because the search space will be, the cross product of the two. But we've done a lot of progress on the computer hardware side, right? So a lot of especially on the edge device embedded systems, this is automated quite a bit. So we can use all the expertise that exists there and then incorporate some of those things in the machine learning design process and the co-design as well.
Okay. So when you combine all these things, neural path, single path, architecture search, the light neural networks, can you talk a little bit about the results you've seen? What were the baselines? What were you able to demonstrate, et cetera?
Right. So in terms of, our models once built, the power and latency models once built, they are just zero cost or constant cost. You just plug in the parameters or the architecture configuration and you get the numbers, right?
Mm-hmm.
So that's, you do maybe a lot of work in the beginning, but then it amortizes across multiple uses. The neural architecture search approach basically reduced the search time by 3 orders of magnitude and more. So we took it from days all the way to hours. And there are many reasons why that was possible. One was the way the search space was defined. The second was how we did the search. And of course, the fact that we shared the structures, parameters across different configurations helped quite a bit as well. So 3 orders of magnitude in the search, meaning training time. And then in the inference efficiency, if you look at the impact of quantization or pruning, you can get maybe 2 orders of magnitude efficiency, especially from quantization. So that's quite significant. We're actually looking now at custom hardware that, post synthesis, post layout, how much of that will translate into the actual hardware. There's still going to be at least 40 to 50% savings that still translates, because the 2 orders of magnitude that I mentioned looks only at the computation. There's also quite a bit in terms of storage that we need to capture. So I think there's quite a lot of good news. So overall, on the training search side, several orders of magnitude. On the inference side, a lot of efficiency from quantization.
On the training search side, do you look at like ablations? You mentioned several different characteristics or several different properties that go into producing your, several order of magnitude advantages in train time. Is that all or nothing? Is there something magical about this combination? Or, have you looked at the individual tricks that you've tried to apply? And, does an individual one of those get you 80% of the way there? How did the different techniques come together?
Right. So I actually think it's the combination thereof, because there are other differentiable neural architecture search approaches, like DARTS inspired. Once you do that explicit representation, unless you do this super network kind of approach, you're not going to get the savings. But at the same time, the ability to consider these specific building blocks allowed us to perform this comparison with MobileNet V2 and V3, right? So I guess you could design your search space differently to make other types of comparisons. The results might be different. But I think the fact that we limit the search space and we also share these parameters across configurations made it for the fast search time.
And so what is ahead in this general line of research for you and your research group?
Yes. So we have not completed the co-design dream yet, right? So because we do have the power latency characterization, we have the, neural network search, we put in the hardware metrics, but do we have a push button solution that we say, okay, my task is this robotic vision application or this AR/VR application, and these are my constraints in hardware, and these are my specifications for accuracy for the machine learning model. Just build for me something that does that. We did not get there yet. What I think is needed right now is to
Even your hardware constraints are relatively coarse, right?
Correct.
The power, latency, things like that. On a typical, an actual chip CPU, for example, you can get tons of metrics and capabilities from the chip itself about, that may impact the way your search operates.
That's absolutely right. And, everything we've done looks at one machine learning model running on this piece of hardware. And that's never the case. There are many more things, even more machine learning tasks running, maybe One does speech recognition, one does image recognition, one does object detection. Maybe there's some sort of multimodal fusion that happens. That's a huge space that we're looking at, right? So I think I guess the goal would be the ability to say, okay, this is what I would like to run. And it's not just one machine learning model. Maybe it's multiple ones. Maybe it's multiple modalities. Maybe it's different tasks, maybe it's the same task with different inputs. How do I run this most efficiently for this particular application? And by application, I mean something that is not a platform. Is, like I said, it could be a robotic or an AR, VR application. So you have the ability to define or design what the platform will be or will look like. So true co-design will happen when we're able to close the loop, right? So we're able to say, okay, this is an initial version of the hardware that I think might work. Based on this, I think your network or networks should look like this. However, when I do it again, it looks like the hardware needs to be tweaked. So it's going to be an iterative, continuous process until you get to the right configuration. The question then stands, well, I'm going to build this, but what if I want to run an additional task on this piece of hardware? Will I be able to do so? So one is the ability to reach this co-design, but the second one is programmability and flexibility. And that's where, there's a balance that you need to, do you want your system to be able to run these new applications? Or maybe it's the same task, but the data set is different, right? You need to retrain it. Does that affect the way your hardware looks like? So I think these are all interesting questions that we're still looking at.
And it sounds like this vein of work is primarily operating under kind of traditional GPU-like assumptions, and there are all manner of other proposed directions that one might go with hardware, from kind of graph native implementations and other things. Do you think these ideas apply similarly to some of those other types of constructs?
Yes, I think that's an excellent question. I think we're pretty much, if you look at the classic machine learning research papers, they do run on typical GPU platforms, right? This is where much of the training happens. This is where inference, maybe inference can be done on, or they provide results on other types of platforms. But I really think, so one is, okay, what are the other options for us to go to in terms of the hardware that we're looking at? So that's where accelerators come into the picture, and there's quite a bit of work on that end. On the other hand, what is beyond neural networks? Neural networks, I think, it's just deep learning has become, I don't know that it's because it's more understandable. I don't think it's that. I think it's because it offers quite a rich field of questions that are still unanswered. But there's quite a bit of other types of machine learning models or modalities that we have to look at, right? Is there any computational impact? Of course there is on those other ones. Is there a role that computer hardware designers or developers should play in that space? Of course they do. But I think right now, if you look at 90% of the work, I think is just deep learning, especially vision, and deep neural networks, neural architecture, search, things that are really well defined, and quite a bit of work happens there. I believe there's still quite a bit of unsolved and interesting questions that have yet to be answered in other types of machine learning that perhaps have not received that much attention because they're not as amenable to be run on GPUs, right? Maybe this is why, there's a chicken and egg. GPUs put deep learning, on the visible end of our attention, but all the others are probably not receiving the attention because they don't really run well on GPUs, which all of us have access to. So I think we can elevate those kinds of machine learning applications by looking at ways to make them more efficient and increase the size and their applicability and dissemination. So I think there's quite a bit of impetus in this field. It's really hard to say. I'm not going to look in a crystal ball and say, okay, in 10 years, everything on the DNN or deep learning side will be solved, and then we're going to look at, probabilistic graphical models or something. I don't know what that might be.
I was going to ask, right?
Yes, right. Well, my students ask me all the time, should I still work in this? Because I don't know if when I graduate, will I still be able to find a job? Um, Definitely. I mean, this is definitely going to be a hot space for high tech.
Though I think this conversation is standing out as one of a couple in the past couple of weeks where there was this undercurrent or suggestion of us being at peak deep learning, which has not really been much of a thing in my conversations.
Mm-hmm.
It's a little bit, that's a lot to extrapolate off of two comments,
Sure.
but interesting that you're saying that. And so probabilistic graphical models is one of the things that you think about as if not a contender, a coexisting thing. Are there others that come to mind as, you're worth?
I mean, yeah, well, closer to neural networks, I mean, you have RNNs that can benefit from much of the things that we've talked about. What I think makes DNNs and actually RNNs as well, or anything that has a deep learning component in it, like, when you look at deep reinforcement learning, it does rely on using or encoding the state action using deep neural networks. So I think the appeal of that is that it's a very well-structured way to look at a problem, right? Because you understand, or we think we understand what the components are. We don't really understand how they work, but we understand what the components do. So I think people are still going to stay in that space quite a bit. What I think needs to happen for others, and I just mentioned probabilistic graphical models because it's really different, right? It's not as structured. And, when people think of AI, there's many other things that, are not quantizable as how many MAC operations can you do in parallel or efficiently, right? So there's more on the decision-making side. And that's what makes it a true AI, right? So I think the gap between where we are now and where we could be is quite wide. I think to see more interesting things happen in other types of machine learning applications is a need for those things to happen more efficiently. And maybe that need is not there yet because we can still perform those tasks using existing approaches. Another way to see an impetus in that space would be to have hardware that supports it, but maybe not because of them, because of some other type of application that is really requiring that. So I think machine learning was the lucky winner of the GPU revolution. GPUs were built in mind with parallelism, and we switched from the single core to multi-core, but then multi-core were not enough, and then GPU came into the picture. So can we envision a trajectory like this for other machine learning applications? Absolutely. I just don't know. I mean, there's many other things that people are looking at. From the hardware side, I know there's quite a bit of interest in removing the memory wall bottleneck, which has been there for quite a bit of time. But to be able to do that, to do processing in memory or to do other kinds of advances in that field, you need help from the technology. So I think maybe the progress in that space might be slowed down because we don't really have a replacement for our current technology, although it's still working quite fine so far. So talking about exponential trends, I mean, Moore's law was supposed to double performance, you name it, transistor density, pick your favorite, every couple of years or every year and a half, and it stopped. But it doesn't mean we stopped in making things more, better and better and more efficient. So there's always something that we can do, and I'm really hopeful that's going to be the case in machine learning as well.
Awesome. Well, Deanna, thanks so much for taking the time to chat with us. It's great to learn a bit about what you're up to.
Thank you for having me.
All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.